In the previous video, I explained NEET previous year questions from 2019 to 2016. And today, I am going to explain NEET previous year questions, NEET or AIPMT from 2015. Okay, the first question. Two similar springs P and Q have spring constants Kp and Kq such that Kp is greater than Kq. They are stretched first by the same amount, case A, then by the same force, case B. The work done by the springs Wp and Wq are related as in case A and case B respectively. Okay, the solution. So in the case A, in case of springs, for springs, we know that work done is equal to half k into x square. But as per the question, in case A, same amount, stretched by same amount, that is x constant, or W is directly proportional to K, because 1 by 2 constant, x is given constant in the question, x same or x is constant. So that implies we can write it as Wp divided by Wq is equal to Kp divided by Kq. If Kp is greater than Kq, then Wp is greater than Wq. This is the first case. And next one, case B, the second case. Again, we also know that work done is equal to average force into elongation. Average force into elongation, or that implies W is equal to half F into E or X, we can take it here. If F is constant, same force is applied on both the springs, then W or F is constant is nothing but for two springs, F can be written as KPXP, or that can also be written as KQXQ, or that implies Kp divided by Kq is equal to XQ divided by XP. From this W is equal to half Kx, so we can write it as W is directly proportional to X because F constant to 1 by 2 constant. So that implies Wp divided by Wq is equal to Xp divided by Xq. But Xp divided by Xq can be written as Kq divided by Kp. Kq divided by Kp. So here if Kp is greater than Kq, then Wp is less than Wq. So here W and K are inversely proportional to each other. This is second case. So in the first case, Wp is greater than Wq. The second case, Wp is less than Wq. So therefore, option D is the correct option. Next question. A particle of mass m is driven by a machine that delivers a constant power k watts. If the particle starts from rest, the force on the particle at time t is. So for this question, solution, in the question only power is given. We know that power is equal to F into V, that is given k watts and it is given constant. So power k watts is constant. But according to Newton's second law, F can be written as ma. F is equal to ma. So here, but F is equal to MA. Therefore, in the place of F, you can write it as MA. A again can be written as dV by dt into V is equal to K, or V into dV is equal to K divided by M into dt. Taking integration on both sides, that implies, so integral V into dV is equal to K by M integral dt. So we know that integral V into dV is equal to V square by 2, that is equal to K by M into integral dt is T, or that implies, so V square can be written as, so 2kt divided by M, or V is equal to square root of 2kt divided by M. From F is equal to M into dV divided by dt. So M into d by dt of V value. So that is 2kt divided by M whole to the power of 1 by 2. Or that implies F is equal to the M constant to root of 2k by M constant. So M into square root of 2k by M into d by dt of t to the power of 1 by 2. That is 1 by 2 into t to the power of minus 1 by 2 according to d by dx of x to the power of n formula. So that implies F is equal to, so you can write M in under root, that is square root of M square 2k divided by M under root 2 into that 2 outside 2, I can write under root that 2 also, so it becomes 4 in the root, and t to the power of minus 1 by 2. So that is equal to, see here M cancel, 2 1s are 2 2s are cancel, so that square root of mk divided by 2 into t to the power of minus 1 by 2 is remaining. So this is our answer. That is option B is the right option. Next question. A block of mass 10 kg moving in x direction with a constant speed of 10 meter per second is subjected to a retarding force capital F is equal to 0.1 into x joule per meter during its travel from x is equal to 20 meter to 30 meter. Its final Ke will be. Solution. Let us first assume that mass is given, velocity is given, so we can easily estimate the initial kinetic energy. Kei is equal to half mv square, that is equal to half into 10 into half into 10 into 10 square. So here 2 5s are 10 cancel, 5 into 10 square is 500 joule. This is the initial kinetic energy. And then work done for small displacement, we can write it as dW is equal to minus F into dx. Here minus F indicates that retarding force. For total work done, so total work done can write it as W is equal to total work done in displacing a particle from x is equal to 20 meters to x is equal to 30 meters. So x is equal to 20 to x is equal to 30 minus f into dx, that is equal to integral 20 to 30, f is given 0.1 into x dx. So that implies w is equal to 0.1, and here minus sign also we should take negative sign, minus 0.1 into integral x dx is x square by 2 limits 20 to 30, that is equal to minus 0.1 into 30 square 900 by 2 minus 20 square is 400 divided by 2. So that implies W is equal to minus 0.1 into 450 minus 200. That is equal to 250, or that is equal to minus 25 joules. According to work energy theorem, W is equal to change in kinetic energy, that is Ke final kinetic energy minus initial kinetic energy, or final kinetic energy KEF can be written as KEI initial kinetic energy plus W. So KEI is calculated in the first line 500 joules minus W is equal to minus 25 joules. That is equal to 475 joules is the final kinetic energy. That is 475 means option D is the right option. Next question. A uniform force 3 I cap plus j cap newtons acts on a particle of mass 2 kg. Hence, the particle is displaced from position 2 I cap plus k cap meter to position 4 I cap plus 3 j cap minus k cap meter. The work done by the force on the particle is. Solution. First, let us take R1 bar initial position vector. R1 bar is given 2 I cap plus k cap, and R2 bar final position vector is given, so 4 I cap plus 3 j cap minus k cap. Therefore, displacement vector S bar is equal to R2 bar minus R1 bar, that is equal to 4 minus 2. 4 minus 2 is 2i, and in the second vector 3j, first vector no j component, so we can write it as it is 3j cap, and in the second vector minus 1k minus of minus not minus of minus of plus 1k, so totally minus 1 minus 1 minus 2k cap. This is displacement vector, and force vector is given in the question. Therefore, directly we can write it as work done. So work done W is equal to F bar dot S bar, that is force vector is given 3 I cap plus j cap. This is the force vector. Dot displacement vector is 2 I cap plus 3 j cap minus 2 k cap. So dot product, that implies W is equal to 3 into 2 6 j, here plus 1 into plus 3, plus 1 into plus 3 is 3, and here no k term in the first vector, force vector, so 0, that is equal to 9 joules is the work done. 9 joules is nothing but option A is the right option. Next question. An object is dropped from a height h from the ground. Every time it hits the ground, it loses 50% of its kinetic energy. The total distance covered at t tends to infinity is. The solution here. Every time the kinetic energy every time it hits the ground loses 50% of its kinetic energy. That is, final kinetic energy half mv square is equal to 50% of initial kinetic energy. Let us assume that initial velocity u, final velocity v. Then here both sides half m cancel, 50 1 ja 50 2 ja, so that implies v square is equal to 1 by 2 into u square, or v is equal to u divided by root 2. In case of collisions, one-dimensional elastic collisions, we have we know that velocity before collision and after collision. So general formula Vn is equal to e to the power of n into u. For first collision, only first rebound. If n is equal to 1, as per the question, n is equal to 1, we can write it as V1 is equal to E into U. If these two are compared with the, we can get E is equal to, by comparing, we can write E is equal to 1 divided by root 2. We also know that total distance traveled D is equal to H into 1 plus E square divided by 1 minus E square is the total distance traveled. So we can write H as it is 1 plus E square is 1 by 2 divided by 1 minus E square again is 1 by 2. So that is equal to 3H by 2 numerator value divided by 1 by 2 denominator value. So both numerator and denominator 1 by 2 cancel. So therefore total distance D is equal to 3H when time tends to infinity. So it means 3H, that is option D is the right option. Next question. In a collinear collision, a particle with an initial speed V0 strikes a stationary particle of the same mass. If the final total kinetic energy is 50% greater than the original kinetic energy, the magnitude of the relative velocity between the two particles after collision is. The solution. Here, collinear collision is one-dimensional collision. A particle with an initial speed V0 strikes a stationary particle of the same mass. That is, first particle of mass m moving with velocity V0. Second particle of mass m, this second particle was initially at rest. After collision, let us assume that first particle of mass m is moving with velocity v1 and second particle of mass m, same mass m, moving with velocity v2. Let us assume that. According to law of conservation of linear momentum, we can write it as m1 u1. So that is mv0. Second term 0 is equal to, so m into v1 plus v2. So both sides cancel. So that implies v0 is equal to v1 plus v2. Or if we can take square on both sides, so v1 plus v2 whole square is equal to v0 square, or that is equal to, so v1 square plus v2 square plus 2v1 v2. 2v1 v2. Let us assume it is equation number 1. And again it is mentioned in the question. Total the final kinetic energy is 50% greater than the original kinetic energy. So therefore final kinetic energy is half m v1 square plus half m v2 square. This is the final kinetic energy. 50% greater what the kinetic energy already have, that is plus 50. So total 150. 150% is nothing but 3 by 2 into half m v0 square, original kinetic energy or initial kinetic energy. So here both sides m in all the terms m cancel, and here 1 by 2 also can take the common on left side, 1 by 2 cancel. So remaining terms v1 square plus v2 square is equal to this side 3 by 2 v0 square. Let us take it is equation 2. Now from 1 and 2, from equations 1 and 2, we can write the v0 square is equal to, in the place of v1 square plus v2 square. Now we can write it as 3 by 2 v0 square plus 2 v1 v2, or that implies 2 v1 v2 is equal to v0 square minus 3 v0 square by 2, or that implies 2 v1 v2 is equal to minus v0 square by 2. 2 v1 v2 is equal to minus v0 square by 2. Now relative velocity, to find out the relative velocity, let us take here v1 minus v2 whole square can be written as v1 plus v2 whole square minus 4v1 v2. So that is equal to v1 plus v2 whole square. Observe here equation 1. v1 plus v2 whole square is equal to v0 square, is v0 square minus 2 into 2v1 v2. 4 can be written as 2 into 2. 2v1 v2 is equal to 2v1 v2 is equal to minus v0 square minus v0 square by 2, minus v0 square by 2. 2 cancel here, minus of minus plus, so that is 2 v0 square. Left side is v1 minus v2 whole square, or relative velocity I can write here. So therefore relative velocity v1 minus v2 is equal to root 2 into v0 is the answer. v1 minus v2 is equal to root 2 into v0. So that is option A is the right option. Next question. The mass of a hydrogen molecule is 3.32 into 10 power minus 27 kg. If 10 power 23 hydrogen molecules strike per second a fixed wall of area 2 centimeter square at an angle of 45 degrees to the normal and rebound elastically with a speed of 10 cube meter per second, then the pressure on the wall is nearly. Solution. Mass of hydrogen molecule is given and number of hydrogen molecules per second also given. First of all, let us take here, see, this you can assume as a wall. It is wall, and when hydrogen molecules hits the wall at an angle 45 degrees, so the molecules definitely rebounds with the same angle with the wall. Here also it is 45 degrees. And horizontal line, if we can take horizontal line here, and there is let us assume that initial velocity v and after rebounds with the same angle, final velocity is also assumed as v. Here v can be resolved into components, that is horizontal component v cos theta of the first incident velocity, and v cos theta horizontal component of rebound velocity. Along the vertical, along the wall, so we can write it as here v sin theta, and here also v sin theta. V sin theta components are cancelled. So here P, that is change in momentum dP can be written as, so mv cos theta minus of minus mv cos theta. So that is equal to 2mv cos theta for one molecule. For n molecules, for n molecules, so dP can be written as 2nmv cos theta, where theta is 45. So this is theta. Observe the diagram. This is theta with horizontal. So with vertical 45 is given, so automatically theta also becomes 45 degrees. And according to Newton's second law, we know that force is equal to dP divided by dt. So that is 2nmv cos theta divided by dt. Now we can substitute the values here. So that implies F is equal to substitution 2 into n by dt. N by dt is given 10 power 23 molecules per second. 10 power 23 into mass is given 3.32 into 10 power minus 27 into velocity is given in the question 10 cube and sine 45 is equal to 1 divided by root 2. This is the F value. And then therefore pressure acting on the wall, pressure on the wall P can be written as F divided by A. So that is here 10 cube 10 power minus or you can write once again here 2 into 10 power 23 into 3.32 into 10 power minus 27 into 10 cube into 1 divided by root 2 divided by A is given in the question 2 centimeter square is given. So that is 2 into 10 power minus 4 meter square. So 2 cancel. Now 10 power minus 4, here 10 power minus 27 is their denominator. So it becomes 10 power minus 27 becomes 10 power minus 23 plus 23 cancel. So 10 cube remaining, or that implies P is equal to 3.32 into 10 cube divided by root 2 value 1.414. So it is approximately equal to 2.35 because 33 by 14 into 10 cube Newton per meter square pressure. 2.35 into 10 cube. So option D is the right option. Next question. A particle capital A of mass m and initial velocity v collides with a particle B of mass m by 2, which is at rest. The collision is head-on and elastic. The ratio of the de Broglie wavelength lambda A to lambda B after the collision is. In this case, a particle of let us here A of a particle A of mass m moving with velocity v and another particle B of mass m by 2 is at rest. Initially it is at rest. Here let us take this is u1. After collision, let us assume that first particle of mass m is moving with velocity v1 and second particle of mass m divided by 2 is assumed to be moving with velocity v2. In this case, according to law of conservation of linear momentum, that is according to LCLM, we can write it as m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. So that implies m into v plus 0 is equal to m into v1 plus m by 2 into v2. So in all the terms m cancel and that implies v is equal to v1 plus v2 by 2, or this can be written as 2v1 plus v2 is equal to 2v. Let us assume it is equation number 1. And again, according to we know that coefficient of restitution can be written as v2 minus v1 divided by u1 minus u2, that is equal to the same numerator as it is v2 minus v1, and u1 is given v, u2 is given 0, that is equal to 1 for head-on elastic collisions. So that implies we can write it as, see here, V2 minus V1 is equal to V. Let us assume it is equation number 2. By solving the equations 1 and 2, that is, first equation, see here, second equation is multiplied with 2. It is 2V minus 2V1 is equal to 2V. So here by adding minus 2V1 minus plus 2V1 in the first equation cancelled. So here it is 2V1 plus V1, that is 3V1, that is adding equation 1 plus equation 2 is multiplied with 2 and then adding. First equation as it is plus second equation is multiplied with 2. That implies we can write it as 3V2 is equal to 4V, or V2 is equal to 4V divided by 3. Similarly, V1, by substituting this V2 value in equation 2, we can get V1 is equal to V by 3. We know that de Broglie wavelength for A, lambda A can be written as H divided by M1 into V1, that is equal to H divided by MV1. You can write it as V1 as it is. And for second particle, de Broglie wavelength lambda B is equal to H divided by M by 2 V2. Or therefore, delta A divided by delta B is equal to delta A by delta B is equal to, here, H divided by MV1 into M by 2 V2 divided by H. H cancel, here M cancel. So what is remaining here? V2 divided by 2V1 remaining. That is 1 by 2 into V2 value. V2 is equal to 4V by 3 into 1 by V1. 1 by V1 is 3 by V. So here V cancel, 3 cancel, 2 1s are 2 2s are. So that is equal to 2 answer. So lambda A by lambda B, lambda A divided by lambda B is equal to 2. That is option D is the right option.